Hey folks, I'm Chuck Black. We're doing 52 weeks of Python and we are in week number 54. That's right, I'm not very good at counting, but I enjoy doing this stuff so much I just couldn't keep from adding a few lessons on at the end. And today's lesson is about recursion. Now we could spend a week on recursion. Well, maybe not a week. I guess these are all 1 week. We could spend 5 days on recursion and you'd probably just be getting used to it and comfortable with it. But I'm going to try to do this in less than an hour. We're going to talk about what recursion is, what it looks like in code, how it works on the computer with this thing that we call the call stack, and putting parameters and local variables onto the call stack and popping it off. When we're done, we're going to look at code that compares two networks and prints out the differences. We're going to look at code that prints networks and prints it out in a nice fashion like this, similar to what Pretty Print does. And I've got news for you, Pretty Print does it recursively as well. So it's a good thing to know this recursion stuff and to understand how it works. We'll also talk about how to make sure that you don't revisit nodes you've already visited, because if you do that, then you will end up in an endless loop that turns into a Stack Overflow, unless you're running in Python where they track that stuff and make sure that you don't do recursion more than like 4,000 times or something ridiculous like that. I've done that and gotten an error, and Python saved me from maybe crashing my VM or my system or something like that. But you do need to be aware of what's going on. You're pretty safe in Python. Hopefully you'll understand this enough in order to not have that type of error. But good news is you will be protected from it if you do. Anyway, enough of me blabbing. Let's get started learning about recursion. Okay, so let's get started talking about recursion. So as you can see, I've created a new module, module 12, called Recursion. In it, I have two separate applications. One of them is called Compare Networks. It takes two networks and compares them to see if they're equal and prints out where they were not equal. And that uses recursion. I've also created an application called Print Networks that walks through a definition of a network and prints it out. In fact, you can see the output of what it looks like here. Now, both of those use recursion. Before we dive into the code, though, we need to look a little bit at what recursion is. So I want to direct your attention to this code snippet that I've gotten. We're going to return to this a number of times, and I'm going to actually expand this in a moment and explain everything else. But the basic idea of recursion is that you will have defined a function, and from within your function, in other words, when you're executing the code for your function, you actually call your same function again. And this, of course, can happen many times. If you do it forever, then you will have a Stack Overflow and your program has a bug in it and you have to figure that out. But the general idea of recursion is that you are calling back into the same function and you are creating a new instance of that function, and you will begin to evaluate it using that data that you get passed in. Now, there's a decent definition of recursion in Wikipedia. So this is the Wikipedia definition. The first sentence here is pretty decent. It says, in computer science, recursion is the method of solving a problem where the solution depends on solutions to smaller instances of the same problem. So if you look at this, then basically we are calling into this function compare data that we're already in with a smaller portion of that data. And so we're going to continue to do that smaller until eventually we get to the end, or to what we would call a leaf node. If you look at this picture here, this is demonstrating the idea of recursion. The idea is here you clearly have a tree, but when you get here and you take this branch, what's this thing that you're looking at? Well, it's kind of a tree. And when you go up here and you take this branch, what's the thing you're looking at? It's a tree. You come down to here, it's a tree, etc. If you were to traverse this tree, if you were a bug wanting to eat all the leaves on this tree, then one way you could do it would be to take the leftmost branch that you haven't visited, and you'd come all the way down to a leaf, you'd eat that leaf, and then you'd go back to the next location and then come down and get the next leaf. Eventually you'd be done with all the leaves and you'd come back and you'd get the next branch, and then eventually you'd be done with that. and you come back and you get the next branch, and then eventually you're getting this next branch, and eventually this next branch, etc., until you've exhausted everything and you're all done. That, in a nutshell, is what we're talking about when we create and execute recursive programs. Okay, so in order to understand how recursion really works, we need to look a little bit at some computer science type stuff, how programs actually work, and specifically about what happens when you call a function. Now, what I'm going to describe to you here with things like the call stack and local variables, instruction pointers, etc., this is not new. This has been around quite a while, ever since I was in college at least, which was quite a long time ago. So this is not something new or a revolutionary new development. This is just the way that it works. And the way that it works is this. There's something called a call stack in different languages, and over time we call it different things, but for right now I'm going to refer to it as the call stack. This is the stack that is responsible for keeping track of the progress of your program, specifically with respect to the calling of functions. So when a function is called, like somebody calls compare data, what's going to happen is basically three things are going to get placed onto the stack, and this can vary between different languages and different implementations, etc., but I'm making this as simple as possible. One of the things that's going to go onto the stack are the parameters that are getting passed. So when somebody calls compare data and passes in a couple of values, those values are going to get put onto the stack. The second thing would be the instruction pointer. That is, whoever called this, we need to be able to resume back where we were. So you need to have that. And the last thing is local variables. If you define any variables that happen to be local, that are only of interest within that function, then there's local variables here. So let's look at what happens in a situation where let's say somebody hasn't called compare data yet. So if somebody calls compare data, what's going to happen is you're going to end up putting another frame onto this stack, and that will contain the parameters that were passed, the instruction pointer of where it was called from, and any local variables that are defined within this function. Now let's pause for a second and look at this. If compare data is going to eventually call compare data, then what's going to happen is you're going to end up adding new things every time you call compare data onto this call stack. Now the good news is eventually you'll get to a situation like in my little code snippet, simplified, where it's not a dictionary, that's what I'm testing for here, and it's not a list, which is what I'm looking for here. It means it's just regular data, and so I do something, and then I return. When I return, do you see what happened? The call stack, we removed that frame from the call stack, and now we're back here with this instance's local variables and this situation's parameters. So we've gone back where we were. If you think about that tree, then we've gone back towards the trunk a little bit to a different branch, all right? And as you continue to do this, whether you go forward or backwards or forward or backwards again, however you end up doing this, you will end up going in and out, and your call stack will get bigger and smaller, and eventually you'll end up back where you were, and then presumably at some point in time you will be done with what you are doing. And so local variables and parameters in these situations, let's just define this. The parameters would be data 1 and data 2. Those are the parameters that got passed. A local variable would be this thing key and value. It's only used within the context of this function, so it's only meaningful right here. And as soon as we pop back, then we forget about those local variables. Now, what I'm not showing you in this picture, but what I will show you when we look at the code, is you can have what we call global variables. So global variables exist outside of the context of a function, and they allow you to store data that is accessible forever for the entire program. And if I was to go back up and do this, you can see everybody has access to global variables. So if there's something that you want to keep track of as you go up and down the stack frame, as we will see in some of our examples, then this global memory becomes useful, and we'll look at examples of that. So this is your quick indoctrination into how function calling works through something like called the call stack. This is really more of an intermediate to, well, it's more of an advanced thing for our class. It's not something that you learn about in computer science until you've been in college for a little while, unless they're doing it earlier these days. I don't even know. But it's a more advanced topic for sure. But I wanted you to have this idea because it's going to be important for you to understand the distinction between a global variable and these parameters, and what happens when you end up doing a return and you pop back to this situation that you were in before. And then when you exit that, you pop back to here and you pop back to here, and eventually you're back at the position that you started at. All right, let's do a walkthrough of this code with my two networks as an example. So let's assume I've called compare data with network 1 and network 2. That means on the call stack, my parameters are network 1 and network 2. And so when we go through network 1, we see that, oh, it's actually a dictionary, and the dictionary is of subnets. So we're going to iterate through these dictionary items. So basically the dictionary items are going to be subnet 1, subnet 2, etc. And so the first time through in this for loop, I'm going to be looking at data 1 with a key of 10.0.1.1 and data 2 with the same key. And we're going to call compare data. Now what has happened is we're going to have something new on this stack. There's a new stack frame, and it has new parameters. Down here we had network 1 and network 2. This time we have the subnet that was pointed to by network 1 with 10.0.1.1, and the other subnet that is pointed to by 10.0.1.1. So we have two subnets that are getting pointed at. Now the next thing that we come down and we do, let's say the next thing is a list of devices. When we call compare data, we're going to be comparing the device at index 0 in network 1, or subnet from network 1, and the device with the index of 0 from network 2, subnet 10.0.1.1, etc. So there's a new, here are devices that we're comparing, here were subnets that we're comparing, here were networks that we're comparing. And then we would end up going down again, and now we're comparing interfaces. And when we're done comparing interfaces, then maybe we're looking at other items in the device dictionary, such as the name of the device, the vendor for the device, the operating system for the device, etc. Eventually, we will finish that device and come back and do another device, which would look like this. Eventually, we'll finish all the devices, and then if there was anything else for the subnet, we would do that, and eventually we would hit return, and then we would be back at this spot. We would presumably be done with what we're doing, and we would return, and all of the call stack stuff would go away. That's the general idea of what the code that we're about to look at is going to be doing. Okay, so let's walk through the code now. I'm going to start with compare networks, and what I'm going to do is I'm going to give you the 10,000 foot high-level overview of this, and then we will dive down into it. So try to comprehend what I'm talking about at the high-level view. This is my recursive function. It's called compare data, and compare data is basically going to come through, and here's the important stuff. If it's a dictionary, then it's going to iterate through all of the items in the dictionary, and depending on whether we can already eliminate it as being bad, then what we're going to end up doing is we are going to call compare data for every item in the dictionary. If it is a list or if it's a tuple, we're going to iterate through every item in the list or tuple, and again we're going to call compare data. And as you can see from up here or down there, basically our contract is that if it fails, we're going to return false. We compare until we get a failure, and then we just return false and go all the way back. We don't attempt to do anything more. If it's a set, we compare the pieces of data in the set. If I haven't really got any sets that we're testing, I imagine you can have a tuple in a set, although I'm not 100% sure, but so I haven't really done anything with that. Don't think I have anything that's a class, but I put it in here more as a placeholder in case you find that you're doing something that has sets or classes in it. Here's where the rubber meets the road. Down here we have a leaf node, so if it's not a list or a dictionary or a tuple, then we come down here and we compare that piece of data with the other piece of data. So that's for comparing things like IP address to the other IP address, and name to the other name, and IOSXR to the other one. So that's basically where we find out if they're equal or not at the leaf nodes of this tree, and if they are equal, we return true, otherwise we return false. That is compare data in a nutshell. This code down at the bottom, and here I'm going to do something nifty. You can collapse these things, so I've just collapsed all of compare data so I can look at, in fact, from lines 8 to 59, it just got rid of them with that clicking on that plus minus sign. So here is my code that does it. And again, I don't want to go into too much detail yet, but we're going to create a network, and I'm passing in the number of devices, a number of subnets, and then I'm doing a deep copy of it. I'm doing a deep copy so that our comparisons will be meaningful. So it's an entirely different copy, although the values are all equal. First time through, we're going to make sure that they're identical. I call compare data. We're going to compare everything, and if I were to scroll down here in my compare data, this would be the first thing. It should be true. It is true, and we compared 320 things. Now this number is going to change because there's variable numbers of interfaces, I believe, in what we create. So it could be higher, it could be lower, but we did a compare data and printed it out. And here's some Python-y stuff that you'll see in action down here in this next one. Now what I'm going to do, because I know what's in the data, the easiest way for me to have two networks that are close to being the same but are actually different is to go and zap one thing. So I'm going to change the name of device number 2 of subnet 10.0.1.0 to silly name, and then it says compare data. It should be false. Sure enough, it is false. It only got to 56 before it found the error. And now this is the tricky part that was difficult for me to do. It took me a while to get this right, but basically I used a stack, and we'll talk about that in a minute. And I'm doing this string join that you may have seen before. You can look it up. It's how you take basically a list and you join all the data, the items together as data, and that's how I end up with this thing, which looks very much the same as what my Python language would be. Network, it's a dictionary with the key subnets. It's a dictionary with the key 10.0.1.0. It's a key of devices 2, name, and then the first case my name is whatever it was, and the second time the name is the thing I changed it to. You can see that matches what we have right here. And so we did that one. Now the next one that I do is I come in and I just zap one of the devices, and so I get rid of that, and then I do a compare data. And when I did the remove item, I did the false. I'd only compared 4 of them. Here's my comparison results. These are all the devices. If you're really good, you'll see here's 1 and 2 and 3 and 4 devices. And if you look at data 2, here's 1 and 2, and there's only 3 devices. So clearly I got rid of one of them. Here is where I actually print it out in a simple fashion. And what I do, since I know that I got rid of a single device, then I'm going to print out device names. So I have remember what this is called? A list comprehension. So I'm just printing this out. And so in my first situation, the unedited one, it looks like that. And in the second one, there's 3 devices. So this is just to help you to do it. Now this is not generic, obviously. Really, I'm going to be working on a unit testing lesson, but these are all basically unit tests to make sure that my code works. Now the last thing I'm going to do is I'm going to say, okay, I'm going to create a network. I'm going to call it network looped 1, and what I'm doing in here that you can't see because there's not space is I'm going to invent for interface 0 on device 10. I'm doing 24 devices, so I'm doing device number 10. I'm creating a new field or a new key in my dictionary called link, and I'm going to point it at my looped network. So here you see this isn't real, but I have a link that's pointing at my same network. And so I'm not attempting to make this a real network. As you guys know, I would have a link and I'd probably have a router and then I would have another network attached to it, but I'm just doing the cheap and easy way. If I were to remove the thing that checks to make sure that we don't have loops in the network, then you would see this fail with a recursion violation. But what's going to end up happening is, as you will see here, if I get down far enough to where it does my looped data, here it is down at the bottom. When I get down to my looped data, I'm going to be printing out whenever I find that there is a loop. And so basically I don't return from doing all my comparisons. In fact, you saw that I had 1978 comparisons. The comparison was true, so it all worked. But basically, if I get down to a node that I had already visited, I abandon. And we'll look at the detail of this code in a minute to see how that works. But basically, this works for hierarchical as well as non-hierarchical, meaning looped networks. Okay, I just noticed a defect in my code, and notice how I'm printing out data 2 but calling it as coming from network 1, and I do that not only there, but I think I do it a little bit later as well. Let's see, data 2, network 1, that's incorrect. So I went over here and fixed it. Hopefully it's fixed, and if we look at this, and I did fix it there, so that's good. And can't remember exactly where all of them were, but at least there I fixed that. So just a note, if you see that in the previous section, my apologies, but I fixed it. Okay, let's look in a little bit more detail at compare data, specifically about these global variables. Now, we haven't made a big deal about this in class, but if you are going to be referencing a global variable, you need to specify that it's a global variable. As you know, Python creates variables names on demand as you type them in and use them. And if you have not said, hey, this is referring to something globally in this module, not something that is local variable here, then it will not work correctly. So this is referencing this thing called a stack down at the bottom of our code here. You'll see that a stack is a list, and every time I go through here, I clear the stack, so we start it over again. And what is the stack? The stack is the thing that is going to create what I have highlighted here. Now, this seems like, well, that ought to be easy to get, but it's less easy to get than you thought, or maybe it is easier than I thought, but I just didn't figure out how to do it. So what I ended up doing, in order to print this out so that you'll know exactly where compare failed, I want to do that, and I want to print out the actual data. So current data, that's going to be current data 1 and current data 2. That's where they failed. And so in order to get all of this, what I do is when I go through here and I found a dictionary, for every value in the dictionary, I append something. That means I put something onto this stack, which is really a list, but we're using it as it's a stack. What do I put on it? Well, I put on the key from this dictionary. So I put in the key and I surround it by opening and closing square brackets. You can see the opening and closing in the text here that I've printed out. If I go through and do compare data and it fails, then I'm just going to return false, and I'm going to effectively leave the stack exactly as it is. I'm going to return false. I will continue to return false all the way out so that my stack that you see goes back to nothing. And so once I'm there, then I have an intact stack that I can then print out and have it look nice. If it succeeds, I don't need that item anymore. If its name and the name was equal, then I can just pop it off the stack. Basically a stack, in a stack, you do things called push and pop. In our list, we can append it to the end, and we can pop it, which basically removes it from the end. And of course, we'll need to do that not only for dictionaries, but also for when we're dealing with either lists or tuples. You can see I do stack.append, and in that situation, I'm appending just the index, like 0 or whatever. Here you see that piece of it right there. That's device number 2. And then, of course, I pop it again. And that's how our stack works. And the current data is just whatever we're currently looking at. So whenever I come into current data, I set my current data, the global, equal to where I am. And so when I exit all the way back out, current data will be set to the last thing that I was at. And that's how we end up being able to print this. This is the last thing that I looked at, which if it fails, that would be the thing that actually, the two items that were not equal to one another. So all of this stuff, for the most part, this part of it is all about making me be able to print this out nicely. Now this last item, this last global, is extremely important, because if we get this wrong, it will cause our program to blow up, or it can if the data, the network that we're getting, is not completely hierarchical but has a loop in it. So all of these things that we've just looked at, those are for basically making me be able to print this stuff out nicely. This one here is critical. And so what it is it is a set that we are creating. And in this set called visited, we are going to keep the identifiers, which is going to be pointers to all of the objects that we have visited. So when we go through all of this recursive stuff, calling back into compare data, etc., if we end up going back and calling compare data with one thing that actually we've been to before, then we will continue to go on and on and on and on, and we'll have a Stack Overflow and our program will crash. So we need to keep a list, which is actually in a set of the locations that we've been, all the objects that we've visited. And what we're going to do is we're going to say if the ID, that would be the identifier, or you can think of it as a pointer to this object, data1, is in this set called visited, or if data2 is in visited, then what we're going to do is we're going to say, whoop, I'll print this out, and then we're going to return, and we're going to say, hey, everything's cool from our side. We don't want it to fail. We're just pointing out we're not going to go any further down this path. And this is how we protect ourselves from recursive loops. Now, you may look at this if statement that's before it and say, why do we have this? Well, here's the deal. The data that we are checking, if it is a string or an integer or a Boolean or a float or a tuple, and I ran into this and had to examine why this was occurring, if it's one of those, then Python is smart enough to reuse that object. So if we have an integer with the value of 10 and we end up using it in many different locations, like here, I'm using it here, I'm using it here, I'm using it here, and probably in many other locations, Python is smart enough not to create a separate object for every single one of these, but rather Python will have my data structure point at this particular object, because remember, these objects don't change. So if somebody was to change the speed from 10 to 10 plus 1, if that was even possible, then what would end up happening would be Python, remember, from everything is an object and the idea of mutable versus immutable, Python will create a brand new object for that. But the object, the integer itself, is immutable. That means it will never change. That means Python can reuse it. And that means when we do this identifier check for something that is a simple constant like 10, then we're going to run into situations where we believe we visited it over and over and over again, but in fact we haven't, because we're just pointed at this particular piece of data. Now, this code that I've written is kind of relatively new, and I've never really used it for any purpose other than for this class. There may be things that I don't even know about this, hidden issues, but this was what I did run into. I can tell you that I ran into this recursive loop, and Python spit me out after it had gotten to like 10,000 or 4,000 recursions deep and said, up, you've exceeded your limit. And Python was absolutely correct to do that because I had inadvertently created a bug in my program where I was looping, and it would have looped forever and then crashed my system if Python hadn't stopped it, or at least crashed my application in a worse way than I would have wanted. So that's why I have this check. Things that are like dictionaries or lists, then I'm okay with going forward and checking to see if it's been visited. Anyway, that is my use of global variables in addition to these parameters that get passed in. Remember, the parameters are new and they are on that stack, this thing right here. They get plopped onto the call stack. But global variables sit out here. They're separate and distinct, and they're accessible by everybody. Of course, globals can be dangerous, so you need to be aware of issues related to that, but they're also quite useful, as you can see from my use of them in this situation. Hey, one thing I forgot to mention, I was so caught up in talking about recursion and how cool that is and all the stuff that was going on. You may have noticed that I am neglecting to follow one of the PEP rules in my formatting of certain things, such as this. See all these return false situations, and instead of doing this on a new line, I'm doing it on the same line. I have so many of these comparisons. You can imagine what the code ends up looking like if I had done every one of these on a new line. It would spread it out. Personally, I like things to be fairly compact and easy to read as much stuff as possible without being cluttered. You'll notice I do favor spaces probably more than other people do, but I do like to put things all the way from left to right and use all the open white space over here as long as it doesn't get cluttered. So I ended up doing that. It is in PyCharm, it will flag it as a violation of PEP standards, but you can go in and say, hey, guess what? I would prefer if you go ahead and not worry about this. And so in this situation, I've already said I want you to not care about this, and consequently it's not putting up a fuss, and I get my favorite little green check mark. But just so you know, it's definitely okay to do that. You may have different coding standards at your company that preclude doing that, but for me this reads a little bit easier, so that's why I did it. Okay, let's look at print networks, which basically goes through a network that has been created and prints it out. As you can see here, the network has subnets. Here's the first subnet. It goes down to devices. Here's the first device, which is a list. The device has certain attributes such as name, vendor, OS, etc. And these are the actual values, so it's printing those out as it goes. You can see when you get down here, you have interfaces. Interfaces has a list, and for every interface there's going to be a name and a speed, and these are the values. So you can see these things printed out in this manner, and it's all pretty straightforward. And I'm trying to get to the end before we actually look at the code. There we go. So basically the code is pretty simple. I call traverse and print, and what I'm passing in it initially is the entire network, but I'm calling everything that it prints a node here. So it's going to be visiting nodes like nodes in a tree. The only global variable I have is visited because I'm not trying to do anything fancy. Here's my check to see if I visited it already, so that if there is a loop, I don't do that. And here's where I add the ID of this node to the list of visited things. Now, as I go through here, here's traverse and print, and you can see it's highlighted for me the two situations where I do a recursive call. One is if it's a dictionary, and one is if it's a list or a tuple. In those situations, I call traverse and print. And there's not a whole lot of extra stuff in here as there was before, although one thing of interest that you will note, when I print it out, what I do in this simple situation here is as I go through, I need to remember how far I have been indented at any particular point in time. And so you can see I'm passing in the current indentation, and then I am using that indentation in order to print this out. So whatever the indentation is, I'm taking a space and multiplying it by the indent. That's how I get X number of spaces, and then I'm printing it out, and that allows everything to be indented nicely so that it looks like you'd kind of expect it to look. So that in this situation, I am passing in the indent, and that makes it nice and easy to do. Now, I do have a different function that is basically the same, except I'm calling it traverse and print flat. And as you can see, what I've done here compared to up here is I flattened everything out. So as long as I'm descending, I don't do a new line, and I just print out the next thing. And then when I finally do hit the end, a leaf node, then I need to be able to remember where I was and go back and print it out. So name, vendor, OS, version. This actually looks somewhat like the pretty print version that you see when you do a pretty print. In fact, I can't remember if this one or the other one I do a pretty print, but it's basically the same idea. You do something different on the first one than you do on the others. You just have to do spaces. And so with that in mind, my traverse and print flat, you can see I've got traverse and print flat recursive calls in here. But basically I need to treat the first time differently and just do this dash dash plus dash. And if it's not, then I do my indentation thing, which gets me to this location. And I will admit, I thought this would be fun and quick and easy, and it actually was quite a pain to do it. Now that I understand how I did it, it of course seems quite easy, but and I won't go through the gory details of remembering where I was, but this is another version of recursive code, but this time we make sure as we go through the list of items in a dictionary or the list of items in a list or a tuple that we do something different the first time through. So here I'm doing something different the first time through than I am on the second time through and the third time through, etc. The code, I don't have as much interesting code here. Basically, I just create the network, and then I call traverse and print and put in a couple spaces, and then I do traverse and print flat, and that's all that I do. In this situation, I do have a question mark. Do you want me to do another? Because I have, as you can see here, I am randomizing the number of devices that I want it to create and the number of subnets. So basically every time I run this, not only will the actual values here be different, but the size of the networks will be different. And that is printing. And you'll see I did actually spend a little bit of time looking at the pretty print code, because of course it has to do things recursively as well. And I did find situations where it's trying to make sure whether it is doing things recursively or whether it's recursing or not. And I don't have the stuff right at my fingertips here, but yeah, here's something where it's saying, is this recursive? So basically it has to do that in order to get this type of stuff to work correctly, basically in order to traverse the entire network of nested objects. In their situation, it's not a network, but yeah, that's how they need to do it recursively as well. And I implemented basically something like pretty print, except with my own formatting and tailored to networking. Okay, so let's review what we talked about in this chapter. We talked about how recursion was basically having a function and then calling that same function from within the function. We took a look a little bit at the definition in Wikipedia and the idea that it's like a tree where you go out to your branches and eventually get to a leaf and then go back to the next branch and the next branch and come back and then go to the next one, etc. That's generally the idea. The way that we keep track of it is via something called a call stack. A call stack, every time we call a function, it keeps track of parameters, instruction pointers, and and local variables that are used and defined within that particular function, and that's how it keeps track as we traverse the tree. We did talk about the two functions that I created, compare networks, where we go through two pieces of data representing networks and compare them, and then at the end print out if there were differences or not. Print networks does a similar thing, except it's not comparing anything, it just goes through the network and ends up calling into itself in order to traverse the tree and to print out subsequent nodes, and you end up with something that looks relatively nice like this. At least in my situation I did. Anyway, that is recursion. Hopefully it made some sense and you're a little bit further along the way to understanding about recursion. It is more of an advanced topic, so if this is new and a little bit difficult, that's okay. As always, if you have questions, then just let me know and I will do my best to answer them. Thanks for listening.